one of the goals of physics is to understand the variety of nature in a unified way. Now, the greatest advances that we've made towards this goal actually are things like when Newton saw an proverbial apple fall. He realized that actually the moon is falling, so he actually unified celestial and terrestrial gravity. Then there was in the 18th century, or 19th century in fact, we had Maxwell, who actually understood that optics, electricity and magnetism are actually the same phenomena. So he had the notion of unifying electricity and magnetism, electromagnetism. In the late 60s and early 70s, there was another interaction which was brought into the unified fold, if you like, and that was work done by a professor also at Imperial College, Professor Abdus Salam, and there with a few other people he realized that the interaction of electromagnetism and weak interaction are actually the manifestations of the same thing. So we got the unification which we now call electroweak theory. These are quantum theories, and what we're trying to do here at CERN and in CMS is to make more progress toward this idea of a unified theory of physics. Now, the next goal is to try to understand how electroweak theory actually fits in with the strong interaction, and at some point try to bring gravity into the fold. Now, to do that, we need to do experiments at very high energies. High energies means actually going back in time. So when the particles start interacting at the design energy of LHC inside the CMS detector, we are going to be creating conditions which existed a billionth of a second after the Big Bang. And so whatever was present at that time, we will try to reproduce here and try to understand what laws of nature were appropriate and relevant there, and try to get a picture to go backwards in time to the early moments of the even earlier moments of the Big Bang. In creating the conditions that existed in the early instance after the Big Bang, we would be producing particles we believe existed at that time. One of those particles is the Higgs boson. So we would like to actually discover the Higgs boson because it plays, or a mechanism similar to the Higgs mechanism plays a fundamental role in trying to understand how mass is generated. The simplest theories we can write down use massless particles. But we know these theories are not correct because we exist, we have mass. So something has given mass to the particles that we are made of. So what is the mechanism that actually gives mass? And the conjecture is that it's the Higgs mechanism. So one believes that there's a Higgs field which permeates the universe, and particles interact with this field and acquire mass, or inertia if you like. And some particles actually do not interact with this field, like the photon, the carrier of the electromagnetic force, which is massless. So that would not interact with this field. Now, this field would be a quantum field, and the quantum of the field is the Higgs boson. So if we find the Higgs boson, we would have established the presence of the Higgs field in the universe. Now, that's one of the aims. Now, it turns out that there are other things which we can expect at the energy scale of LHC, which is the center of mass energy of the proton-proton is 14 TeV. Now, the other phenomena could be things like a symmetry which we believe nature has used, which is called supersymmetry. It relates spin half and integral spin particles. And the prediction of this theory is that for every particle we have a superpartner. For an electron we'd have a superelectron, for example. And since we have not found superelectrons yet, they are probably massive, and the LHC will probably find them if supersymmetry is relevant at the energy scale that we will be probing. That means we'll have another set of particles to discover and study. There's also the notion that gravity should be brought into the fold. Now, gravity is very weak. Why is it weak? Now, if you try to unify in a conventional way all the forces, gravity actually becomes as strong as any other force at a very, very high energy scale, which we call the Planck scale. This is 10 time with 19 zeros behind it, GeV. So it's a very, very high energy which we'll never be able to achieve in experiments on the Earth, for example. Now, one possibility that people have put up is that actually we don't live in 4 dimensions, we live in 10 dimensions. And in fact, when you look at the law of gravity in 3 dimensions, we have the normal formula, which goes as 1 over r squared. But if we were to live in only 2 dimensions, the formula would be 1 over r. So the number of dimensions modifies the law of gravitation, and in fact other laws as well. So if we live in higher dimensions, actually gravity is just apparently weak, but actually at some energy scale, which could be the energy scale of the experiment that we're going to be doing, gravity actually manifests itself in more dimensions. And one of the manifestations would be that we would create mini black holes in the experiment. And these black holes would have a very, very characteristic signature which we'll not be able to miss. And this will come out within the first year of operation, for example, or first 2 years of operation. So the energy scale at which the LHC is going to operate and the CMS is going to operate is really a very fundamental scale. It is not any other scale. It is a scale at which something must happen. Now, one other way to actually understand this fundamental nature of this energy scale is we have a standard model of particle physics. In fact, we should call it the standard theory. And it is probably the crowning achievement of 20th century science to set up this standard model. We have tested the standard model at energies 10 times lower than the energies that will be available at the LHC, and the predictions of the theory match the experiments in 1 part in 10,000 in almost any parameter that you can think of checking. So this theory is very successful, but we know that at the energies of LHC, this theory breaks down. It gives mathematical nonsense. Probabilities of some processes occurring go beyond 1, which is nonsense. So we know the theory is not right at 1 TeV, center of mass energies, if you like, or constituent center of mass energies, which is 10 times higher than, for example, LEP was, which was the previous generation of experiments here at CERN. So we know something is going to break down, and one of the possibilities is actually the Higgs particle actually regulates, we call it in scientific terminology, this aspect of nonsense. So this energy scale is very fundamental. To make progress in physics towards unification, this step must be taken. If we do not take this step, then this branch of physics will just become metaphysics. So these experiments, CMS and the sister experiment that is ATLAS, are really very fundamental to make progress in this area of physics and perhaps in science in general.